Okay, the last one got cut off here, so let me just go over what I had. It just didn't resume recording when I thought it would resume. So here's the function we're given for the position as a function of time, and they say t is greater than or equal to 0. That's not really going to be important. They often do that, I think, because they don't want us to worry about the past, be forward-looking. I don't know. It kind of bothers me because it gives students the idea that the past doesn't exist, which it really does. Anyway, it's not going to bother us here. The velocity, derivative of position with respect to time, that's another notation for it. And that's just, if we just take the derivative, it's 6t squared minus 30t plus 36. The acceleration is derivative of velocity with respect to time. Or another notation for it, I don't think I've happened to mention this explicitly in class, is d squared s by dt squared. The d squared means do the derivative. That's kind of what the d is indicating. Take the derivative twice. Oops, don't want to move it. And then the t squared, you might think, well, what's that? I'm not differentiating with respect to the quantity t squared. What it really means is for both of the derivatives, take the derivative in t. It's really a shorthand for one more thing, which is d by dt of ds dt. It says take s, take its derivative, put it into the d by dt, its derivative with respect to t, and then take the derivative again with respect to t again. And that's clarifying that each time it's a t. So if you really follow this literally, it would be d squared and then d squared t squared on the bottom, but they just leave that to be a d. Okay. So it's also s double prime of t, you could call it that, and it's 12t minus 30. The next part of the problem just says plug that in at 1, just for fun. And the units here are meters per second squared. The units of v are going to be meters per second, and then the units of the acceleration are, you take the meters per second, which came out of meters for s over seconds here, and then you plug it into here, you're going to be dividing by seconds again. Because remember, the units for a derivative are always the units of what's on top, in this case that's meters per second, divided by the units of what's on the bottom, which is seconds. And so here's a of 1. Then the last part, they say, at the instance when the velocity is 0, what's the acceleration? So these happen to be turnarounds for this function. If you actually carefully plot this like we did on the test, it's very similar to the test problem. There's two turnarounds, and when you're turning around, when you're changing from one direction to another, you're probably accelerating. And that's what we want to figure out. In what direction are you accelerating and how strongly? And so you set v equals 0. There's the v function. You can divide it by 6 and then factor, and you get the 2 times when the velocity is 0. And then all it is plugging that back into the a formula. And we get an interesting fact. They're equal and opposite. That's not true for all functions with 2 turnarounds, but it turns out to be true for all cubics. It's a kind of a cool fact about cubics, is that the acceleration, if the position is a cubic function of time, the accelerations are going to be equal and opposite at the turnarounds. Okay, now I'm done.